Cellular networks have become a way that the majority of the world, probably accesses the internet. But what's not necessarily realized is that cellular networks differ in many ways from the sort of traditional internet that we grew up on. And these differences cause problems for protocols and applications. So one of these differences is that cellular networks are very variable in the link speed that they expose to applications. So this is a recording we took in Boston. We drove around one night with a Verizon LTE cell phone, and we just recorded. We saturated the uplink and the downlink. We kept them busy, and we just recorded how fast did packets transit the network. You can see it's extremely variable. It's up at 1,500 kilobits per second, and then down to something like 200, then suddenly up again, and then down, and up and down, and up and down. And this is not like old-fashioned Ethernet. Another way these networks differ from the sort of old-fashioned networks is that they're too reliable. We talk about best effort network delivery, but that's kind of a misnomer. This is like way insane effort network delivery. So this is a trace we took, again on Verizon LTE, just doing one TCP download, just one download, and we look at the round trip time just with ping on another flow, and you see we get these insane delays because TCP, fills up the buffers in the network. That's sort of its job. And so every other packet, it could be audio conference or video conference, has to wait in line. So we get a 2-second delay, 3-second delay, even a 10-second delay. And this is a well-known problem. But again, it differs from sort of what applications may expect. So as a result of these differences, we see that interactive applications, especially video conferencing, audio conferencing, they perform poorly on these networks. We know this sort of anecdotally, but we set out, my coworker, I should say this is joint work with my colleague and co-author Anirudh, he's there, and our advisor Hari Balakrishnan at MIT. We set out, Anirudh and I, to measure this quantitatively. So we drove around Boston with 4 different cell phones, measuring 4 networks from 3 commercial providers. And we saturated the uplink and downlink of these networks, and then just measured when did packets manage to get to the other side. We took those traces and put them back in a trace-based emulator in our laboratory. It's just a box with 2 Ethernet cards. It takes in packets on one Ethernet interface and queues them, and it releases them from that queue just according to whenever packets were released in the trace. And then over this emulated cellular network, we ran various commercial video conferencing programs, including Skype, Google Hangout, and Apple Facetime. So let's just take an illustrative look at the highlighted ones. We'll look at Skype over the Verizon LTE network. So here we see on the top the throughput, and at the bottom we see the delay. So if we zoom in a bit here, you'll see the black line on top. The network is actually quite good. We have like a megabit per second, but Skype is not using it. Skype is way too conservative. The video quality is worse than it could be. And even when the network gets good, Skype doesn't use it. And yet what we'll see is that as the network deteriorates, Skype is no longer so conservative. Here about 1 minute in, the network has gotten worse, but Skype, the red line, has not slowed down its transmissions quickly enough. So in this case, Skype has overshot the available capacity, and the consequences are devastating. We build up a huge delay here, like a 5-second delay. So this destroys the possibility of interactivity because Skype is trying to do sort of a slowly variable rate control, and that's just not possible here. So if we had to summarize the performance of Skype on the Verizon network, we're going to make one of these delay versus throughput plots here. And there's going to be a lot of them in this talk, so I'll explain it. The throughput's on the y-axis, so up is better. And the delay, we flipped the x-axis, so the better delays are to the right. So up and to the right is the best. That's the least delay and the most throughput. And Skype here does not do so hot. It seems to average about 1 megabit per second. I guess you could have a video conference at 1 megabit per second, but the delay is more than 1 second. That's just not going to cut it if you want to have a conversation with someone. So that's Skype. Why is the performance so bad? We think it's because these existing schemes are primarily reactive. They wait for a signal of congestion. Could be packet loss, which these days does not happen very much on these cellular networks. Could be an increase in the round trip time. But what we find is that by the time you get these signals, it's just too late. You've already overshot the mark. And the real killer is this self-inflicted queuing delay that, as we saw, it builds up these large delays, and you get these stalls, and can you see me now, et cetera. Even a small overshoot can cause these large buildups. So we made our own protocol called Sprout. Sprout is a transport protocol designed for real-time interactive applications over these kinds of variable, semi-reliable networks. Sprout has an explicit goal. The goal is to provide the application with the most throughput possible, but the more important priority is to bound the risk of accumulating a large delay. So that's the main constraint. bounded risk of a delay. So what do we mean by that? How do we assess the risk of the delay? We have a sort of a three-part algorithm. At the receiver, the Sprout receiver, we try and infer what is the current link speed. You know, it goes up, it goes down. We do this probabilistically. We're not certain. We'll talk about that. Then part two, we try and predict what's going to happen to the link speed in the future. So we don't want to wait for congestion. We actually want to model the variability of the network and try and react even to the risk of congestion, of a decrease in link speed, even before it's happened definitively. And then part three, we have a control strategy where back at the sender, we want to send as much data as possible, but not so much that we'll have more than a 5% risk that a packet will be delayed more than 100 milliseconds. So that's the control strategy. And I'll talk about these each in turn. So the inference. Why do we have to infer the link speed? Why don't we just see the link speed? This is another case where these cellular networks differ quite a bit from the traditional sort of Ethernet. On an Ethernet, if it's a 10 megabit per second Ethernet, I send you MTU-sized packets. You're going to get those at wire speed, you know, basically a packet every millisecond. These cellular networks don't have wire speed. And if you do this experiment, if you flood, again, this is Verizon LTE, this is a stationary phone in the middle of the night with no one around. You saturate that link. Even so, you see a huge disparity or dispersion in the inter-arrival time. So what we see here is a histogram of just the amount of time between adjacent packets received. Still, the most common inter-arrival time is 1 millisecond. So this is about a 10 megabit per second link on average. But the actual arrivals of packets is not isochronous. They're not all the same amount of time. It's more like a Poisson process, like atomic decay. And it's actually even worse than a Poisson process. It's very heavy-tailed. This is like a flicker noise process. In fact, it's so heavy-tailed, we even had one inter-arrival time was almost 4 seconds. So that's, you know, pretty rare. You're getting packets 1,000 times per second, and you see nothing for 4 seconds. I mean, these are really heavy tails. So even just figuring out what the current link speed is, you can't get it exactly. We have a probability cloud, or a probability density function of, you know, what the link speed could be. That's part one. Part two, now we're trying to predict from our uncertain probability cloud of the current link speed what's going to happen to it in the future. So we have a model that the speed of the link, what I showed you in that first slide, that it evolves according to a random walk, or Brownian motion. It could go up, it could go down. And the farther in the future we get, the more that cloud of probability, the more uncertain it gets. And the receiver then makes a cautious forecast based on this evolving cloud to figure out, at the worst case, how many packets is it safe for the sender to send? So by worst case, I mean the 5th percentile. So how can we be 95% certain that if the sender sends this many packets, they'll get cleared by the network? The receiver makes that forecast, piggybacks it on an ACK back to the sender. And in reality, almost all the math is pre-calculated. So we don't really do anything fancy at runtime, but we talk about it this way. So the model, we have a stochastic model, and this is the diagram. We model the link as there's a sender. He sends packets to the queue. The queue is drained according to one of these Poisson processes. And the rate of the Poisson process itself varies. This is the link speed. And it's this parameter lambda, the link speed, that we try and infer. We have certain parameters that we've hard-coded into this model. You know, the volatility of the random walk of the Brownian motion is in our case, it's fixed. It's just a particular value. You know, if it gets into an outage, that's sticky a little bit. We're trying to hit a delay of 100 milliseconds. We have a 5% risk tolerance for exceeding that. So these are our parameters. But I should stress, this entire model and all of our source code was frozen before our data collection began. So these are not trained or tuned or skedaddle. There's no funny business here, but this is the model. We're not saying that this is what cellular networks do. We're just saying this is what our program does. So that was the prediction. Part three is the control strategy. Back at the sender, we have this cautious forecast that the receiver has given us. We have to decide how many packets to send. We do that by looking 100 milliseconds in the future, and we see, okay, how many packets can I send that I think they'll be cleared by that interval? So I send 50 packets. Now we go in the future again. We can look 100 milliseconds in the future, and more packets can be sent. And we can look again 100 milliseconds in the future and send more packets. So this combines pacing with windowing and with these statistical techniques so that even without learning again from the receiver, we can still send more packets because we surmise with 95% confidence that they will be cleared by the network. All right, so how well does this scheme do? I showed you that trace again with Skype. Let's look at it with Skype and with Sprout. So still the black line on top is the capacity of the network. The blue line is now our algorithm, Sprout. And as you can see, we do a much better job profiting from when the network is good. We get more throughput that we can make available to the application. And yet, when the network deteriorates, right here, you'll see Sprout has already figured out what's going to happen because we're conservative and we're actually below the network capacity. So unlike Skype, which has this overshoot and builds up this large delay, the blue delays, our delays, are less than 100 milliseconds almost all the time. So that's the empirical behavior of our system on this trace. So if we summarize the behavior of Skype, we said it was here, and let's look at some other schemes. We tested Facetime and Google Hangout. These are all kind of the same. Google Hangout has considerably better delays. It's only like 300 milliseconds, but the throughput's really bad. We also tested delay-based congestion control strategies, LEDBAT, Vegas, Compound TCP, and these are better than the video conferencing rate control strategies. We also looked at, just what about the default TCP in Linux and Android, which is cubic. That's quite different. That gets great throughput, but horrendous delay. So not really good for a video conference. You don't want to be waiting more than 5 seconds. So what is Sprout? Well, surprise, we're not necessarily the best because cubic beats us on throughput, but we're definitely the best on delay. So if you were going to do a video conference, this would be the one you would want. And you might say, well, what if I want better throughput? I'm willing to give up a little bit of delay to get better throughput. Well, we have an algorithm for you. We have a more aggressive version, a simpler version, Sprout EWMA, that gets even better throughput than cubic with less delay. So that's one trace. We tested 8 of these links. So this is the Verizon LTE downlink. I'll show the other links. The thing to look at is whether the blue algorithms, that's Anirudh and me, are we in the upper right? And so here we are on the Verizon LTE uplink. Again, the blue meanies are in the upper right. The Verizon 3G downlink, we're beaten here by cubic on throughput, but generally the blue guys are in the upper right. Verizon 3G uplink, blue guys doing pretty good again. Here's AT&T downlink. Here's AT&T uplink. Here's T-Mobile downlink and T-Mobile uplink. So you can see the scheme, even though the model is very simple, fixed volatility, constants, drawn out of a hat. In practice, it works quite well. Overall, compared, for example, with Skype, we achieve more than twice the bit rate on average and a factor of 8 reduction in delay. Compared with Google Hangout, we get more than a factor of 4 improvement in bit rate and a factor of 7 reduction in delay. The only parameter we lose on ever is against cubic, where we get something like 10% less throughput, but we have a factor of 80 improvement on delay. So, I would take that. But you have a choice. You might say, well, this is not quite fair because, Facetime is probably not trying to maximize throughput. They have a certain megabits per second they want to send. They're not trying to get more. That's totally valid, but there's no excuse for Facetime to have 9 times more delay than it could have. I mean, Facetime probably wants low delay. We experiment, what if we twist those knobs a bit? So instead of a 5% risk tolerance, what if we allow 25% risk of more delay, or 50 or 75? And we get this nice curve here that suggests that there really is a delay versus throughput trade-off, that maybe the application or the user might want to twist the knob. If you were watching me right now, you might not care about getting within 300 milliseconds. You might be happy to wait 5 seconds, or even 10, to get a higher quality version of me. So we like the idea of these knobs that can adjust the trade-off. Another surprising result, people say, well, this problem of, that these networks are so reliable, we call it buffer bloat, it really needs to be fixed inside the network. Instead of maintaining this queue indefinitely, Verizon should use active queue management. So we should persuade Ericsson to implement a new AQM algorithm, and then Ericsson should sell that to Verizon, and it should be inside the LTE base station and inside the baseband chip of the Android phone that has the queue for the uplink. That manufacturer should implement this algorithm. People say this is the way to go, the active queue management. Active queue management is great, but what we found is that for this kind of application, it may not be necessary because we compare Sprout and Sprout EWMA against TCP cubic running over the Cottle AQM algorithm, which is recently published by Van Jacobson and Kathy Nichols. And we find, in fact, our scheme, which is entirely end-to-end and involves no LTE base station changes, is competitive with the method that requires intrusive router changes. So we think this is a surprising and provocative result, that perhaps it is possible to fix these problems on the endpoints, at least for this kind of application. You might also ask, what about competing traffic? What if I've got TCP competing with Skype? And in fact, you can tunnel those both within Sprout. And in fact, if you're willing to put them all through Sprout, you can, let's see, in this competing case, you can improve the delay seen by Skype by a factor of 35 and the throughput by Skype by a factor of 6, but the cost is that your TCP throughput gets cut in half. So, there's a cost of fairness, but this is something else we can do. In February and March of this year, the Stanford networking class, they have the Reproducing Network Research blog, which I think is great, and 2 students there actually reproduced some of our measurements, some of our results, and they were awarded the Best Project Award in the Stanford networking class for reproducing our results. I think that's good. I hope it doesn't mean that we were the most difficult to reproduce, but I think it's a good thing. But, we thought if Stanford students are going to get an award just for reproducing our results, MIT students, we should give a prize for surpassing our results. So we did that. In the MIT networking class, we've held a contest, which is still ongoing in the MIT networking class, and so we packaged up our whole evaluation and our whole trace-based emulation system into an Amazon EC2 image. And we gave the students, a container that represents the sender and one that represents the receiver, and we said, go wild, write whatever sender and receiver you want, and there's a script to evaluate it. And see how you do. You can use Sprout and vary on that. You can do a new thing. We have some crazy machine learning grad students in this class, and they did some truly crazy things. And we had prizes. We said 4th place, $20, 3rd place, $30, 2nd place, $40. And then if you actually beat Sprout, there's the grand prize, which is that you get to be a co-author with me and Anirudh on our next NSDI paper. And when we announced this, there was something of a pause in the class, and they asked, could we just get the money? But I think this is awesome, and I hope that they beat us. We haven't finished the results. But we have preliminary results from the sort of training phase. This is the baseline that we gave the students. Again, it's a delay versus throughput graph. Here's Skype, not so hot. Here's Sprout, which has got about the delay that it's supposed to have, about 100 milliseconds, and the throughput is respectable, 3.5 megabits. And here's the omniscient algorithm. This is literally the best you could do if you had complete foreknowledge of the network trace in advance. There was no uncertainty about what's going to happen. So the students, there were 40 students in the class, and they tested 3,000 protocols over the course of this contest, probably twiddling knobs on them. And we have results on all of them. So here they all are. This is the land of 3,000 protocols. Here is every protocol the students tested. We think this graph is quite provocative because it suggests that there is an achievability region. Theoretically, the queuing theorists have not gotten around to solving these kinds of problems. But empirically, if you regard MIT students as able to search the space, this suggests that there really is a region of compromises that are achievable. And if you look at the convex hull of what the students were able to achieve, there's a sort of range of optimal trade-offs. And we're happy to see that Sprout, even with no tuning or training, is on the frontier of that range. And that suggests really maybe you cannot beat Sprout. You might be able to get better throughput. You certainly can get better throughput, but you must accept more delay. Or maybe you can get better delay, but you must accept less throughput. Perhaps we really are on the frontier of some sort of achievability space. It's not clear. There's a lot of limitations to our work. We only evaluate the case of a video conference, a long-running flow. We're not talking about web traffic or transients. All of our measurements are in Boston. We ask the user to wrap their competing flows inside Sprout, because if you run TCP outside Sprout, if the queue at the base station is full of someone else's packets, so there's a 5-second delay, there's not a lot any end-to-end protocol can do to jump to the head of the line. So we can't fix that problem. Fortunately, cellular networks have per-device queues, so the problem is really local to your own. If you can solve the problem on your own cell phone, you've solved the problem. But other networks like Wi-Fi don't have that thing. Wi-Fi has a shared queue. Typically. So in an end-to-end system, you may require changes in the network to solve this kind of problem in Wi-Fi. People ask the question, what about when the cellular link isn't the bottleneck? What if it's somewhere else on the internet? So what we would say, bottom line, our approach, what we think is novel here and why we get these kinds of results is, we pick a model, it seemed reasonable, but all models are wrong. But they help anyway. We found it was helpful to have a model. And then we just try it, and we see if it lands on what seems to be the frontier. Not on a single network trace, but on a large set of traces and newly collected traces. And the idea that we could package up the evaluation of schemes seems very provocative, because it means we could, I've been at MIT a long time, but I recently learned that of the smartest people in the world, most of them actually are not at MIT. So it seems like, why would we only collaborate with people at MIT on this? We should just make it public. Anyone can try and improve a congestion control scheme or anything. We should have a sort of continuous improvement, a Kaizen for congestion control, and we should post it out there, and anyone should be able to collaborate with us, and we should just find the best scheme for these kinds of cellular networks, and it could evolve over time. So that's where we think this is really going, is that we could find better models and adapt them to real schemes. So we'd like to acknowledge our shepherd, Lakshmi, and the students who helped us, and Andrew McGregor, who gave us the idea of this flicker noise process. So to summarize, we have this Sprout algorithm. It infers the current link speed in uncertain probability cloud. It predicts what's going to happen to it in the future. Its uncertainty will expand. And it tries to control the risk of large delay by using this cautious forecast technique. And in practice, this achieves dramatic gains, much better throughput, and much lower delay compared with the existing rate control schemes in existing real-time interactive applications. It also can even match the gains seen in active queue management without making any intrusive router changes on this kind of application. The code and directions to replicate our results or try our results or collect new data are all available at alfalfa.mit.edu. It's a draft website, so if you have questions, we're happy to help you. Please email us. I'd be happy to take your questions.
Hey, Phil, Stanford University. First of all, fantastic talk. This is absolutely awesome. So I was really pleased to see you had LEDBAT in there. And so I'd actually sort of move on that and say, so LEDBAT was designed to solve a subtly different problem, but do you think that you should replace LEDBAT with Sprout? In the sense of, I don't want to increase the delay for competing applications, using this as a background transport protocol?
That's a good question. I think LEDBAT tries to coexist with TCP on the same bottleneck queue and sort of scavenge available bandwidth. In this paper, we just have not tested when you compete with TCP on the same queue, or in fact, when you compete with anything on the same queue. So I don't want to say that we would do better than LEDBAT in that situation. I do think, LEDBAT has some similar techniques in it. Like I think they may have a Kalman filter, and they have this one-way delay estimation, which we also have. So I think there's a lot of spiritual similarities between us and LEDBAT. But other than the case where you're alone on the queue, I can't say that we're prepared to replace them.
Thanks.
Hi, Curtis Heimerl, UC Berkeley. So I have two questions. I'm going to try to make them brief to give people time. The first one is, have you thought about using sort of geographical knowledge to help with this? Like, we know what that fall-off is on your throughput graph. It's you're switching towers in your car, and you might be able to use that to make better predictions.
Yeah, I think there's some previous work at NSDI by Banerjee and probably many other people on this kind of thing. I don't know. We would have to try and see, like, if you know my current position and heading and speed, does it help? So anytime you want to talk about enhancing the model, we have to ask, does it help? I don't know.
Okay, and the second question is, as these are cellular networks, there is a whole circuit-switched piece of technology that essentially is designed to solve this question for voice traffic. How does that relate in terms of like what you think the problem you're solving? Is this something that they could just solve by doing calls over that circuit switch network?
Well, the circuit switch network, I think in a cellular system tries to give equal, there's an admission control system to give you a certain amount of bits per second. And if they can't take your 64 kilobit per second call, they just don't let you make a telephone call. They don't have that for large bitrate flows or flows that would need to vary in speed. So I'm not sure how. I think this problem of the link quality varies. I mean, that's a fundamental problem with these cellular networks. I don't think you can just solve it with better policies. I mean, sometimes the network is good and you want good quality video then, and sometimes the network is bad and you want bad quality video then. I do think they could do a lot by just not queuing these packets forever, but I don't know if you've talked to these phone company guys. You say, like, why don't you just drop some more packets? And they say, well, right now we have 5 nines reliability, and you're asking us to have fewer nines reliability. They really interpret their reliability goal on sort of per packet basis, and it's hard to get them to change.
Okay, thank you.
Hi, Costin Raichu, Polytechnica Bucharest. So, looking at your graphs with the available link bandwidth, even if the mobile is stationary, you'll get that. But the reason you get that is because the base station is allocating the throughput dynamically to the number of users. Okay, so the other users are presumably running TCP, so you're in a sense trying to track what the TCP allows you to use, right? I'm just wondering, have you tested Sprout against Sprout? I mean, how does the curve look when Sprout is doing this, right? Because you could have interesting interactions.
We certainly have tested it. We have a configuration. We have 6 telephones, and we put them all on the same cell. And then we have one guy running, and then we bring up a second phone and have him start blasting, and a third phone have him start blasting, and fourth. And we look at the effect on the first phone. So we do test that kind of configuration.
Hi, Sultani from IAI. I'm wondering, have you looked at DCCP transfer protocol? Have you compared your?
You'll have to correct me if I'm wrong, but my understanding is that DCCP has a sort of pluggable architecture, and you can have TCP-friendly rate control and more TCP-like rate control just plug into it, and it will control your UDP. So I don't think they have their own congestion control scheme, is my understanding.
Well, because actually you have the graph up there, because when that incident happened on DCCP, usually if you have a packet loss resilience, then you don't see those peaks there. So your problem is solved.
I'm not sure. Sorry, I don't understand.
Well, basically, if you have, because for like real-time video, correct? It's
why don't we take it offline?
okay.
I have a question about the theory behind this. Do you know what's the status of that work? Can you, for example, prove that you're insensitive to the parameters that you chose randomly?
Theoretically?
Yeah.
No.
Is
No,
that just too difficult?
Well, we are
or?
sensitive to the parameters. I mean, we assume that the volatility is 200, and if the volatility is less than that, or if the motion isn't Brownian, our predictions will be less accurate.
Can you prove, is there any other work on the theory behind it that would help you?
Well, there's libraries about queuing theory, but this question of, when you have a general, they talk about MM1 queues. I mean, this is a generalized admission queue, and
Right.
the service process is unknown. I mean, it's whatever real life does. So you're talking about trying to find the best policy for arrivals at a queue whose service process is ill-specified, and you only get delayed feedback. That's a very hard problem.
Thanks.
Thank you very much.